Our next session for the day on the topic Quest for Distillers Corn Oil. I'll take a moment before welcoming our next guest speaker. I would like to introduce her, Ms. Tara Vigil. She is the Vice President and General Manager of Bioprocess Solutions at Trucent Separation Technologies, LLC, a chemical engineering and petroleum refining graduate from Colorado School of Mines. She leads efforts to deliver advanced separation technologies to the ethanol, rendering, and fats and oils industries. With over 20 years of experience, she brings expertise in engineering, project management, business development, and innovation. A very, very warm welcome to you. Can we welcome her with a huge cheer, everyone?
Well, good afternoon, everybody. Thank you to Jima for the kind invitation to speak with you today. It's a great honor. Today I'm going to be talking to you about corn oil production, or DCO production. Trucent, in 2008, we developed a corn oil separation system for separating distillers' corn oil for ethanol producers. We call this COSS technology, or short for corn oil separation system. And there's about 95 installations in North America. We provide ongoing sales and service, and because of that, we've been able to collect a lot of data from our customers. And we collect this data, and it helps us to improve our design, but also it helps us to work with our customers closely on their efficiencies. Today, in India, we're partnering with Crab and Tower to provide those same services. So what is DCO? DCO stands for Distillers Corn Oil, and it is a product of corn ethanol production. You might be surprised if you've never seen it. It's actually reddish orange in color, not typical like corn oil you might see on the shelf in the grocery store, but it really has the same physical characteristics. And it's a very high quality fat that can be used as an animal feed ingredient. It's not intended for human consumption, however, but it's generally recognized as safe. So what is it used for? We can use North America as an example because it's a very established market. In North America, the uses are renewable diesel, biodiesel, and in the animal feed industry, and then it's also exported to markets for other uses. This is an example composition. Where does it come from? The oil comes from the corn. We can only extract as much oil as we started with. We're not making oil. It comes in with the corn, and this is just an example of a typical corn in the US is about 62% starch. Around 4% of that is fat or oil that we can extract, 15% moisture, and around 19% fiber and protein. So why do we recover it? The reason is, Hugo alluded to that, it's very profitable. It really makes the margins in the plant. It's an extra co-product, and it is actually the most valuable product in an ethanol plant today. It's about twice as much, or it gains about twice as much price as ethanol does itself on a per pound basis. So here's an example of some of those prices. Today, this is today's market. Ethanol goes for about 25 cents. DDGS around 8 cents per pound, while DCO is a little over 50 cents per pound. So really profitable, and it really makes the margin in the plant. What's driving that in the US? What's really driving that is the growth of the sustainable aviation fuel industry, but particularly the renewable diesel industry is really driving the growth because DCO is a very valuable product for that industry. So I'm going to switch gears and talk to you a little bit more about how this is produced in an ethanol facility that produces ethanol from corn. There's a lot of different variables that affect how much oil you can extract. It's not just how much oil is in the corn, but it's how you operate your plant. Hundreds of variables, and over the last 17 years, we've gathered a lot of data that's helped us to understand all of these variables better. So like I said, the corn yield it can be affected by a lot of things, not just the corn, but what's the viscosity of the feed going to your centrifuge? Things like, what is your feed flow rate? Others like, do you have a hydro heater or not? How much free fatty acids are you creating? Other things like, what is the particle size in your whole stillage? How are you grinding your corn? What is the hold time you have before your system? So many different variables. What are the enzymes you're using? What are the chemistry of the demulsifiers that you're using? All of these things affect how much oil you can extract ultimately. But we can simplify that a little bit. Today I'm going to talk and focus really on 3 areas. Where we start is at the corn itself. Like I said, we can't make oil in the ethanol plant. We only can take the oil that comes in with the corn. So that defines how much we start with. Then we can look at the second place. Where can we lose the most oil first? And that's at the decanters. So the decanters that occur after distillation, where we're decanting the whole stillage into 2 separate streams, the wet cake and the thin stillage. That's the first potential place for loss. And then finally, the next place would be at the extraction itself. What are the efficiencies that you have across your system, and what are you doing there? So where is that in the process? Let me try this here. So, like I said, the corn starts at milling. That's where we define how much oil we have. That's in the corn kernel itself. And then the next place here is after distillation, where your decanters are, where you're separating that whole stillage into those 2 separate streams of wet cake and thin stillage. And then finally, let me go back. The next place is here at our centrifuge, or your corn oil separation system itself. And that's typically after you've concentrated that thin stillage that you separated in the decanters in an evaporator, and that becomes the feed to your corn oil separation system. So we can look to North America as an example of a developed industry that's doing corn oil production. As Hugo mentioned, everybody's doing it. And the reason they're doing it is because it is so profitable and it really makes the margins in a plant. So let's look at the report card. How are we doing? So this is taking into account typical production in North and South America. Industry average for what are the yields that we're seeing across the plant for corn oil production is around 1.9 pounds per bushel of corn. But the leaders are doing better. So that's the average, but there are those who are doing better, doing upwards of 2.1 pounds per bushel. I'm pretty sure the Impasa plant is doing a lot more than that, yes? So the leaders are doing better, and how are they doing it? Because they're paying attention to all of those variables. Particularly also at the decanters. We can look at that second stage that I told you. What happens at the decanters? We're splitting into wet cake and thin stillage. And so at the decanters, we talk about the split. And so if I say the industry average is 60% split, that means 60% is going to thin stillage and 40% goes to the wet cake. The leaders are doing this a little bit differently by adjustments in their decanters and how they operate. They're having a 75% split. And so that means 75% goes to the thin stillage and 25% goes to the wet cake. And then let's look at the third place that I said, where the efficiencies across your machines. So industry average is close to 90%, which is really great. A lot of advances have happened in the last 18 years to get to that point. However, the leaders are still doing better. Some of the leaders are getting 96% and even upwards of that, close to 100. Yes? Yes, Hugo's nodding his head. Some of the leaders are doing 100%. So I want to switch gears today and talk to you a little bit, how do we do this? What is the basis? I'm going to do a little bit of a little class here on separation theory for a moment for you to understand, how does a separator work? Well, I'm going to define a few terms and then we'll talk about how it works. So when I say feed, that's the mixture of the solids, water, and oil that's fed into the separator, or the stillage that's concentrated in the syrup. That's your feed. The light phase is the liquid that's obtained in a separator that has a density that's lower than your feed, and that's the DCO. So that's what we call the light phase. The heavy phase is the liquid that has a density that's higher than the inlet product. So that's the de-oiled syrup. And then the separation zone is the place in the bowl that determines where the light phase and the heavy phase are separated. And then sediment is the solid particles that are left over. So we can look at it like this. How does separation theory work? It's all based on specific gravity. And what is specific gravity? Specific gravity is just a number, a fluid's number relative to water. So we take specific gravity of water as 1, and then we look at the DCO, or the corn oil. Corn oil has a specific gravity of 0.85 around. So what does that mean? It means that it's 85% as dense as water. So it's lighter, and that's why it floats. Then the solids have an average around 1.3, and that means that it's heavier, and that's why it sinks. So basically, if we look at this in a simple way, if I had a big tank, a settling tank, and I put this mixture of solids and water and oil in it, what would happen? The heavier stuff would sink and the lighter stuff would float to the top. And that's really what separation theory is. It just means heavy things sink and light things float. And that's really the basis of how we separate the oil. So if we think about that tank that I just talked about and we turned it on its end and we added some acceleration, what would happen? So basically inside of this, we use a bowl and it spins at really high speeds. And this spinning really creates a really strong centrifugal force that's thousands of times greater than just gravity. And then inside of the bowl, we have a disc stack, a series of discs, of conical discs, and they are really the key to the separation efficiency. We divide the liquid into layers of those discs, and that's what drastically reduces the amount of time for the particle to travel and be separated. So what does that look like? That's all culminated into what we call a disc stack separator, or a disc stack centrifuge, it's sometimes called. And it's a machine that really just rapidly speeds up that natural separation process. So instead of just relying on gravity alone, we rely on the centrifugal force of gravity. So an example of how that might feel on your body, centrifugal force is the same thing like when you're turning your car and you feel your body go the way with the car. That's the feeling of the force of gravity. This is another example of military training where they put really strong high G-force on pilots, for example. This is another example of how strong that gravity force is. So let's look at that in action. How does that work inside? First, we put the mixture or the feed into a spinning bowl. And then we add that centrifugal force that flings the dense particles or the solids to the outermost part of the bowl. Then what happens is the less dense liquids, which is the water and the oil, they're forced outwards, but in separate layers that are closer to the center. And then the heavier parts, the heavier liquid, which is the water, will be further out than the lighter liquid, the oil. And the conical discs are what really makes this all work. The solids slide down the underside of the disc to the edge of the bowl, and then the separated liquids travel up and down the channels that are created by those discs, those stacks of discs. And then finally, the separated components leave continuously through the separator out of different outlets. All of this is guided by Stokes' law, which is a mechanical, it's an equation, a complicated equation, but we can break that down into simple variables. And it really just states that the speed at which a particle settles in a fluid is really dependent on the size and density, viscosity of the liquid, and the force of gravity, or in this case, the much stronger centrifugal force. The disc stack separator manipulates these factors to make it much more rapid separation. This is an example of a corn oil separation system. This is Trucent's system. It's a turnkey system. Like I said, it's in operation in over 95 systems in North and South America in over 40 ethanol plants. And really the advantage is the high speed, and that's really what makes this work. Another thing about this particular system, or Trucent system, is it's optimized for DCO production. It's the only one in the world that is. The disc stacks themselves, the discs are designed specifically for corn oil only. So over the 17 years of Trucent partnering with our customers, we've learned a lot of things, and we've learned a lot about those variables that I showed you and what affects them. So I wanted to talk to you today about our experience and give you some best practices. And really some of those are really, I'm just going to talk about pre-treatment and setting up the centrifuge for success, process control, and then also data collection and trending. So first, one of the best practices we really need to focus on is particles and viscosity control. And if we look at Stokes' law again, we can see that viscosity is a variable that we can affect. And what affects that when we look at particles and viscosity is grind at the mill. How fine of a grind will affect that, lowering the viscosity and helping you to have a cleaner centrifuge also is part of that viscosity control. Size really does matter in separation. One way to affect that is to put in something like a brush strainer ahead of your centrifuge. It helps aid in the separation because it removes those larger size particles and reduces the viscosity. This is an example. This is Trucent's brush strainer, but there are other designs in the industry. Ours is specifically designed for DCO, and we have many multiple size screens that we use to adapt to the various conditions at everybody's plant. So it's different for every plant. Here's an example of the results after installing this in 3 different plants. You can see that it reduced the viscosity differently at these 3 different plants because they have different feed conditions. And so every plant will have a different result, but putting this in front of your centrifuge allows you to increase your yield by up to 7%. This is another example of that as well. The TruShield that I just talked about, that brush strainer, it's inherent inside of Trucent's design of that modular system that I showed you. But we also have one that's standalone that can go in front of anybody's system. And we've seen really great results with that too. So this is showing that viscosity reduction and then the average increase in oil that those plants saw, which was very significant. Next best practice is dosing. Dosing what, you might ask? So in the production of corn oil, a demulsifier chemical is required in order to inhibit the creation of an emulsion. But it also does some other things too. It also coalesces the droplets, and I'll talk about that in a minute. But some of those best practices that I'll talk about are bench testing regularly so you know how well your demulsifier is working, making sure that you have a good injection point or a place where you're injecting this chemical and getting good mixing, making sure that you have the consistent dosing, making sure that you have a consistent ppm across your feed. And then also ensuring that you have good mixing, that you don't have stratification, and that you have the optimal pH for whatever demulsifier you've chosen. So we can look again at Stokes' law. This again is the governing principles of separation theory to think about demulsifiers too. What we're trying to affect in the variable in the equation now with the demulsifier is the droplet size or the diameter of the droplet. And you can see that it's squared in this equation, which means it has a much bigger impact than the other variables. So that's why your demulsifier is important. And so if we look at under a microscope, here, you see how these droplets look very small? Well, once you add the demulsifier, one of the points that you're trying to do is make those droplets bigger. And so after a demulsifier, You see like over here how that's coalescing into these big droplets, and that makes it much easier for separation. Another part of ensuring that we are working well with our demulsifier is making sure that we're operating at the right temperature and right timing, the amount of time to allow that demulsifier to do its work. And so a lot of plants, we recommend to put in what we call a heat and hold system, which means making sure you get it to the right temperature for the demulsifier that you've purchased. And you can see at a lower temperature, the viscosity is greater in syrup. And so at a higher temperature, you'll reduce the viscosity, which helps in the separation and also aids in the coalescing. Another point, best practice about dosing is to make sure that you have a consistent parts per million dose of that demulsifier and adjusting your dosing to your feed conditions. So a lot of people have feeds that are not consistent. And so how do you maintain a consistent dose is to make sure that you have automation to adjust that dose with the feed. We do have a system that we use for that, which adjusts the feed up and down, or not adjust the feed, adjusts the dosing up and down with the feed automatically. And you may not know that demulsifiers are the same chemicals that are used for emulsifying. So if you overdose, it's really bad because it's not only are you wasting the chemical and spending more money than you need to, but overdosing isn't necessarily a good thing. Not saying I'll get better demulsifying if I just add more. If you add too much, now you'll create an emulsion. So a lot of these emulsifiers are used, think about candy making. The same demulsifiers are used in making candy. Think about your favorite candy bar and the nougat. They use emulsifiers or demulsifiers just at a greater rate to make those candies. And we don't want that. That's very hard to separate. Another best practice is making sure that you have a clean centrifuge and clean piping and a clean system, clean brush strainer. Our system, we have a clean in place system that's automated. I recommend that for all systems. We have a co and counter current flow, and it ensures that the whole thing is clean, including the brush strainer and everything inside of the machine, and all of the piping and the decant piping and the light phase piping. Why do you want to do that? Well, remember I talked about those stacks of discs, and the gaps in between them are how the separation occurs. Well, if those gaps are filled with dirt and grime or solids, then you're inhibiting the separation, and that's why CIP-ing your system routinely is important. Another best practice to think about, we call it taking a heavy cut or a dirty cut for yield improvement. So we can use an example of a salad dressing bottle that you might have a familiarity with from the grocery. And in this example, we can think about the same separation that we were thinking about with the tank or the settling tank. But in your salad dressing, it's more visible. We can see that the oil floats to the top, the solids are floating to the bottom, but we have this kind of emulsion layer here of the salad dressing that's in between. And you can see some of those solids are floating in there. Well, those solids are carrying the oil still. Some of that oil is still bound in that solid. If we take a heavier cut, that means we take some of that dirty solids that still have oil with it, so we get more oil and we increase our yield that way. How do we do that? We can adjust the gravity discs to make them move the interface inward, and this pushes the heavy liquid outward, so some of the heavier phase gets pushed into the light phase. And you can only do that if you have a system to be able to handle that. A system like, we call it a true oil concentrator system, but this is really a decantation system. And so it's an automated decant where you're able to take that heavier cut, get some of that dirtier solids, and we settle it out, and then we have a decantation step. This allows you to have cleaner oil, but it also allows you to get that higher yield improvement and also send those solids back around to the front of the system and give another shot at recovering that more oil. Final best practice I wanted to talk to you about is being data-driven. And I really can't emphasize this enough. It's about making sure that you take the samples and do the analysis in all the other parts of the plant that affect the corn oil system, because it's not just the corn itself, and it's not just your efficiency across your centrifuge. You have the ability to affect your yield in other places in the plant, but you're only going to be able to do that if you're sampling and you have the analysis to be able to compare day to day and establish those baselines. So where do you test? First spot would be at the corn flour itself. The next spot would be at the whole stillage that we talked about here. Going to the decanters. Then we want to know the composition of the wet cake and the thin stillage. Also before your heat and hold, or where you're dosing, and then after you're dosing. So, and which would be before you have a brush strainer and after the brush strainer. And then after it goes through the system, we want to test the heavy phase, the light phase, the de-oiled syrup, and then the final product after the decantation step. What do you test? So in those spots, what do we want to test? So in order to get that baseline and understand how you can affect the process at the corn flour and the whole stillage here, and the whole stillage that's coming from the beer stills going to the decanters, we want to know what is the percent oil. At the wet cake, we would like to know what's the percent oil, but also what are the solids, so that you understand what is going with those solids and what is that fat content that's going into the wet cake. Thin stillage, we would want to know similar things. We want to know the oil and the solids content, but we also want to know the composition of those solids, what's suspended and what's dissolved, and that's going to help us understand how to adjust that brush strainer for particle distribution and get rid of those bigger solids. But we will only know how to adjust that if we take the sample. A volumetric spin, I didn't mention that, but that's really a simple way, a visual way. You just take a spin through a lab centrifuge, and you can see, is the oil on the top? And you can get a visual of what everything's happening as a more routine test. You know, when you take these other tests maybe once or twice a day, but a more routine test, you can just take a quick spin and get a very quick visual. Other places that we'll test, what do we want to test at the syrup after dosing and the syrup after the heat and hold? We want to know a lot of the same things. What is the percent oil? What are the solids? And then what's the composition of those solids? So we know how to adjust our downstream system. At this point, we've added the demulsifier. So, excuse me, at this point, we would want to look under the microscope and be able to see, is our demulsifier working? So we would want to ensure, excuse me, I need some water. We would want to ensure that, thank you very much. Sorry, it's dry. Thank you. Yeah, so at this point, we want to look under the microscope and see, is our demulsifier working? And we would want to know, and we could know that by the size of the droplets, are they coalescing together or not? And then we'd also take a syrup after that viscosity reduction. We would want to know what is the viscosity and what is the pH, because there will be an optimal pH for whatever demulsifier you're using, and so you want to make sure that you're within the range. Finally, the heavy phase, we would want to know, we could look under the microscope again. So the heavy phase is what is not the DCO. It's everything. It's what's going to the de-oiled syrup. So you don't want any oil there. So we would want to know, a volumetric spin is a quick visual. Is there oil layer at the top? That would mean you need to make some adjustments because you don't want any oil in that heavy phase. And we could look under a microscope too to see, are there any droplets of oil. Then we would, of course, want to test the light phase. We would look volumetric spin there, but the finished DCO is where we would really want to know what is the solids, what is the moisture, and we can do another volumetric spin. And then refined DCO, that's a whole nother topic I could talk to you about later. But that I didn't really go into that. That's something that you could do further after making DCO to make it more applicable for renewable diesel, in particular by removing metals and free fatty acids. But that's a completely different process, and so you would require different tests there too. So really, in summary, about the best practices, particularly this one, it's really important to take the data. You can't make any adjustments if you don't know what's happening in your plant. And so we really highly recommend that you do these analysis before and establish that baseline so that you'll be able to make those adjustments and achieve the highest yields. And that is my summary, and I appreciate the opportunity to speak with you, and I hope you learned something, and I'm happy to answer any questions that you might have. Sorry.
We're open for questions.
What kind of demulsifier? Is it anionic, non-ionic, cationic? And generally the food grade demulsifiers, they are produced from corn oil itself. So how do you actually choose which is the right one? It's a very tedious, too much bottle testing, and so.
Yeah, so there are a lot of varieties of demulsifiers out there. At its simplest form of a demulsifier, it would be, most all of them are polysorbate 80 based, meaning that's the base chemical in that, and then there's a lot of things that are added to make it more beneficial for this case.
Actually,
silicon is added.
No, some of them are not food grade, but the polysorbate 80 is a pharma grade. Mm-hmm. And the biggest problem with polysorbate 80 is that it's a very high tendency of emulsifying rather than demulsifying.
Sure.
Unless you add the sorbitol.
Yeah. So the experience in the United States, however, is that the basis for nearly all of the demulsifiers that are used in corn oil production is polysorbate 80. And then other chemicals are added and other additives are added. I'd say most of the most successful demulsifiers have silicon as part of their composition. And that's our experience.
Good morning. Yeah, I have a couple of questions.
Sure.
So the US went through a phase where the DDGS prices went down when a lot of corn extraction, oil extraction was going on. So can you just tell us about like how much rates went down, like in terms of in the DDGS? And the next question is, I saw in one plant where they're doing germ separation and doing oil extraction right at the beginning, and doing germ separation before milling. Mm-hmm. And so is that the right approach?
Understood.
Excuse me, I would like to add to this question. I would be more interested in the economic numbers of separating the oil. How much weight we lose in DDGS and how much price we lose in DDGS.
Sure.
So how economic sense it makes for us to separate the corn oil.
Right. So I can't answer what the economics will be in India, but because it's just starting, right? And so you're going to be in the initial phases here. In the North American market, there was an initial drop in pricing of DDGS, but it has recovered, and the DDGS prices are what they were, if not more, than fat without fat. Not all of the fat is removed, so it's considered a lower fat DDGS because of what I showed you before, that split that occurs at the decanters. So, you know, an average plant would have 40% of the oil still going into the whole stillage, into the wet cake, which goes to the dryers and becomes the DDGS, and that gets concentrated more. And so typically we'd see a maybe 6, 7, 8% fat in the DDGS in the US. And the market adjusted. The market adjusted. It's such a high protein, high value product that the same pricing that you would get for the higher fat is the same as the low fat. And the economics of the DCO itself are so incredible that the market, the ethanol producers are demanding those prices, and the farmer or the feed industry recognizes the DDGS as such a valuable product too for its protein content that they're willing to pay. And so I think initially maybe you'll go through that same market experience, but the value is still there. The value is still there. I'm sorry.
The second question was some people are doing germ separation and extracting oil initially itself. So can we do that as well?
Sure. There are people who are doing that. A lot of that is happening in wet mills in the U.S., doing it upstream and getting the oil there, and then it can be food grade. It requires typically more capital to do it at that point in the process. Our systems are, I would say, not even just our systems, the majority of systems in the United States, probably over 95%, are at the after the decanters, after the concentration of stillage.
Hello.
Yes.
Ms. Tara, I want to know one thing. Indian corn has 3 to 4% oil. How much you can extract on base of corn? 1 ton corn has 3 to 4%, 3.5% we 3.5% we take average. How much we can extract out of your things?
Sure. So typically, it depends on all of those factors that I shared with you. And so a lot of that has to do with the plant themselves and how they are operating the plants and all of those variables. But I would say on average, like I showed, it's 60% of what you start with. So 60% of that, 4%.
60% what is in corn, right? 2.4, that means 2.4.
So if the fat were
If my corn has 4%, then
Correct.
you are saying that 2.4 will be extracted.
Correct.
Are you right?
Yes.
Okay, very good area. Because we are being offered here 1.3. You are saying 2.6. What we are being offered, the recovery is 1.3 out of 4%.
Sure.
So there is a really a good thing to see that these machines. Second thing, here everyone is selling the horizontal machines, saying they are saying decanter. Yours is vertical machine.
Vertical, yes.
With the disc operating over there, just like starch separators and other separators. So what do you feel that these are less, there is a less maintenance in your machine as compared to them, or is there more maintenance in your machine? Runnability of time will be another essence for us.
Sure, sure. I think that, again, depends. But the horizontal machines, you know, there's pros and cons to both. Horizontal machines have sometimes they're a little bit more robust in terms of accepting high solids or mistakes and able to accept a little bit more challenge. However, they're less efficient, a lot less efficient than a disc stack centrifuge. And so proper maintenance and proper operation, you're going to get more yield. And the price of distillers corn oil, at least in North America, it really drives the efficiency. And so the maintenance overall, it's different, I would say. I wouldn't say it's more or less, it's just different because of the differences in the design.
I think there will be less maintenance in your machine, isn't it?
It's different maintenance. So our machine requires annual maintenance plus a routine preventative maintenance quarterly. But it's very small maintenance and it's very quick. It takes less than half a day to do it. We have service technicians that do that for our customers, and we're establishing a service group here with Crab and Tower to do that in India. The maintenance on a horizontal is different. It's annual typically, but it's more capital intensive. So it depends on how you look at it. It's just different.
How you feel India is going to be your market in future?
For me?
Yeah, for you.
For Trucent?
Yes.
We are hopeful. We see India as really the next frontier for corn ethanol. And it's been so refreshing to be here today and be invited and to see what great strides you've already made here to achieve the blend rates that you have in such a short amount of time. And we hope to be a resource to you. That is our hope.
So you set up the office, you set up your service center here, then
Yes.
you will definitely get the breakthrough within the Indian ethanol industry. Thank you very much.
Thank you, sir.
Hi, Tara. You mentioned at some point in your presentation that a finer grind is essential to increase your yields. In how many plants or installations in the US do you see a secondary grind as part of DCO?
More and more plants are doing a secondary grind between liquefaction and mashing. That's very popular and very effective for yield increases in not only oil, but ethanol as well. I think Katzen could probably answer some of those questions for you as well about the secondary grinds, and I know their plants have that in them, and it is effective. But for oil production, that's helpful, and the secondary grind actually releases more oil, some of the bound oil that's in those solids, but it also creates that finer grind so you don't have those large particles going into the separator. It just helps everything. The brush strainer, a finer grind is better.
Any more questions from the audience? All right. I think we'll conclude the session with this. And I think we've continued with more engaging discussions and more interesting questions and thoughts which have come up post your presentation. So, Ms. Tara, I extend our gratitude to you and your team member for joining us. Thank you so very much. Please let's give them a hand. Please have a seat.